So today we'll talk about the series RLC circuit and some, initial and final values of it, plus whether it's under, over, or critically damped. All right. So now we have instead of a step current input like we had for the parallel RLC, we have a step voltage. Same things though, is before this edge, it's acting like DC, and after this edge, it's acting like DC. And in the middle, right here, I'm calling that high frequency or infinite frequency because frequency is a change in time, right? And this is like an infinite change in an infinite amount of time, or an infinite change in an infinite amount of zero amount of time, excuse me. So that's a lot of change, so that to me has a lot of frequency. Now, sure, if you take the Laplace of that, you get 1 over s, and then if you set s equal to j omega for the Fourier, you realize there's a lot of frequency in there. So let's just summarize our impedances. So for the resistor, it's R, and it's an ideal resistor. A non-ideal resistor does have inductance and capacitances, right, which you can just model by adding them on in series or in parallel. So it doesn't matter what the frequency, resistance is resistance. For the capacitor, though, if F is 0, or effectively 0, right, the impedance goes to infinity. And when the frequency is very high, it goes to 0 or a short. And the inductor is backwards. So at 0, it acts like a short, and at high frequencies, it's infinity. So let's look at the before the edge, right? The resistance is the resistance. The capacitor goes to infinity, so I take it out, right? And ZL is 0, it's a short, so I just redrew it there. Now, no current flows because it's broken. VR is 0 because there's no current flow. And what is V in? Well, it was set to 0. So actually, V1 equals V2 equals V3 actually equals 0. All right. Now, why or what would happen after the edge? Well, now the input is 1, or Vn, if you will, right? So the picture is the same, except so there's no current flowing. This is shorted, right? There's no voltage drop here. So everything is equal to Vn now, or V1, depending on how you want to manage it. So if I were to sketch this out, right, I would start out here, it'd be 0, right? And then at some point, and finding the actual, how long it would take, a little bit involved. But we know we start here and we're going to end here. Now the trick is what kind of shape is going to take us there? Are we going to have this kind of shape, this kind of shape, or this kind of shape? Well, the one that's oscillating is underdamped. The one in the middle is critically damped, and this longer one is overdamped. Now, just to give you a heads up, the way they fall in order here, you have to understand that for this circuit, 1 over LC is the same for all of them, for that kind of relationship to be true. So let's do the damping. So again, the easiest way just to tell whether it's over, under, or critically damped is just to look at things, impedance, right? And just with no input. So just short it, right? Because when V in is 0, it's a short. Now, when a current source is 0, you take it out because they're infinite impedance. So this lends itself to mesh because there's one loop. So VR plus VL plus VC equals 0. I times R plus I ZL plus I times ZC equals 0. Now the I here, right, that can't be 0. Otherwise, nothing ever happens. Um, some faculty say it's boring, right? So I just get rid of it. But also you can do it algebraically as well. Now here, this equation is correct, but it's not very helpful for finding what we need. We need to get it into this polynomial form, right? So I multiply by s over L, and I get s squared plus r over ls plus 1 over LC. Okay, so really, s is it depends on the situation, right, of what you're doing. But s is a complex number, and this would have roots to it, right? What values of s would make it equal to 0? And based on those kinds of roots, or what kind they are, we don't even have to calculate what they are right now. We can determine what the system will do. So here's the quadratic equation, right? But really, this part here is going to tell us what kind of roots we're going to have, because this will be a real number, right? So it's the plus or the minus that's going to determine it. So if this term, r over L squared, is greater than 4LC, I'm going to get plus or minus a real number. I'm going to get 2 real roots. That's overdamped. Now, if they're equal to each other, I'm going to get plus 0 and minus 0. So that's one repeated root, right? That plus and minus square root of 0, it's there. It's just not one simple root. And that would be critically damped. And if this is less than 4LC, then that would square root of a negative number is an imaginary number, and we would get plus or minus some imaginary number. Imaginary numbers or complex numbers come in pairs, or complex roots come in pairs, and that's under damped. So what does this really mean? You know, graphically, if I were to try to sketch it. Well, we know that we were going to start here and end at Vn in this system. We just don't know how we're going to get there, right? So with an overdamped system, that's proportional to 2 separate exponential decays because it's got 2 different roots, right? And one will be bigger than the other, and you'll kind of get this slow kind of shape, all right? When it's critically damped, it's proportional to t times 1 exponential decay. Now these equations, there's more to it than that, but I'm just saying at the heart of it, 2 exponential decays. Here, time times an exponential decay for the critically damped. And again, for the underdamped, you have another exponential decay, but it's being multiplied by a sinusoid. Again, there's more to it than that to get it to match. But that's what you would be looking for in your system. So that's a pretty straightforward way of looking at an RLC circuit, right? Now, yeah, there are let's just redraw it here. Using voltage division, right, I can find V1 over V3 equals ZC, ZR plus ZC plus ZL, right? And with some algebra, that can be shown to be here. And now you would find where this was equal to 0. Later on, you'll find out that when the denominator is equal to 0, we call it a pole. all right? But essentially, that's the same kind of characteristic equation of the denominator that we found with just doing the impedance method, right? So we do this a lot in 110, but really, if you want to know what something's going to do, it's very easy just to short the inputs or take the inputs out of the equation or picture, okay? For example, here's a bonus. Um, let's say I had this circuit. And you want to know how long it's going to charge or discharge, right? So obviously, whatever's here, right, will be amplified to be out. And you can do, for that step thing, you can still do the same thing, is that before the edge it's DC, after the edge it's DC. And so what would happen is you'd actually open that up and you would see that there's a voltage division here um, to get that input because that Vx is at a virtual ground, right? So that's not so much about that problem, but the time might be hard to see, right? So let's short the input. And you might say, all right, that's RC, right? Tau would be RC because, you might think, well, the op amp is acting as a buffer. And it does. However, this is at ground, a virtual ground. Current does flow into that resistor. Now, yes, this is true. In this example, the current in here is 0, so the tau is RC here. But now notice, all right, that's tied to ground, that's tied to ground. Let's redraw it even more. And I'm just going to say, all right, now everything's in parallel, right? Which then I can even redraw like this and call that R1 in parallel, R2. And now what is tau? It's R1 in parallel with R2 times the C. So even this simple thing um, can be used to analyze, pretty complex circuits, right? But because of that voltage division, I try not to use this configuration when designing things, but it might happen to see it on an exam near you. Anyway, have fun.